types of candidates.
Yeah.
What, some of
The one that Lila was saying. Not that one. That's not what you were saying.
That's the one I have been seeing this whole phone this whole time.
But you've been.
The
Oh,
model-
I
When
you walked in.
Modern general, information vegetable, animal, and mineral, and the quote device historical.
Yeah, but it's just.
It's really fast.
It's the. That's all. That's in my head. I don't know what he's
I'm not ready
saying.
for this play.
Okay.
Are you gonna be in it?
Probably.
What?
No, we need people in it.
They should open it to teachers.
I'll be a policeman.
Rhea Logan was the placement.
Or Ruth. There's
That's
a.
fine.
All right, here we go. We got only a few minutes here. So we're gonna continue talking about solutions here. Can you guys give me just some common solutions that you know very well?
Salt water.
Okay.
Kool-Aid.
Oh.
Kool-Aid.
That's a pure substance.
Kool-Aid.
Kool-Aid, sugar water, salt water.
An alloy.
Yes.
Molten metal.
Steel.
Yeah. There's an alloy. Yeah. How about the atmosphere?
Also.
Also, like carbon dioxide dissolved in pop. Carbonated.
Isn't water kind of a, like,
It dissolves like minerals in it.
yeah, because most of the time it's not.
Okay.
Like tap
You
water.
said H2O. You didn't say tap water. Okay. So obviously, when we're dealing with solutions, there are things that are dissolved in other things. Okay. We know solute dissolves in solvent to produce solution. Okay. There is a cardinal rule when it comes to solubility. Do you guys remember it? You look at your notes, but yeah. Do you remember that? The whole idea that like dissolves like? And
Yeah.
When we talk about like dissolves like, what?
Polarity.
It has to do with polarity. Okay, so what
Non-polar.
dissolves what?
Non-polar dissolves non-polar. Polar dissolves polar. That's why oil and water don't dissolve each other. Because oil is non-polar and water is polar. Or vice versa.
You don't know which one's polar?
Water's polar. I do the stupidest of the kid
And you could add to that. Because that's just the most extremely polar version, right? Okay? Now, wait, did I try that? I think I did. So there, I assume that is in your notes, right? Okay, so there is a process that is involved for dissolving something, and they come up with a 3-step process, and it really is an assumption. I don't know if they haven't figured out fully what actually happens, or because it happens all at once. I'm not sure, but this is their theory as to how dissolving happens. Okay, the first step is the solute needs to be separated. So if I've got like a clump of salt, it would need to be what? Right? It needs to be broken up into its individual ions in order for it to be dissolved.
That's why warm water or shaking it would make it dissolve faster.
It helps, yeah. But there's more factors than just that. But yes.
More science.
Number 2, overcoming intermolecular forces in the solvent to make room for the solute. Well, as you guys can probably imagine, if we're talking about water, there's intermolecular forces. What type of intermolecular forces are within water? From last chapter. It's one of the 3 types.
Hydrogen.
Dispersion.
Hydrogen.
Hydrogen bonding. Oh boy.
Dipole.
That was last year.
I'm a failure.
Yeah, we already took our semester test on that. We're done.
Yeah.
So you're done with that, yeah? Smack you on video here.
That's on camera.
Yep.
Where is it? Camera.
That is on camera. Okay. So obviously you got to make room for the solute to go in between the solvent. So in order to do that, you're going to have to break or expand the solvent as well. And then the third step would be allowing the solute and the solvent to interact, or have the solvent surround the solute and dissolve it. Okay? So it's really a three-step process, but obviously from our experience it appears to happen all at once. Are all three of these steps exothermic? Are all three of these steps endothermic? Are some of them exo and some of them endo? Could you tell me? Do you even remember what exo and endo is?
Yeah.
That was last semester.
What do you think?
Number 3 could be either, or is it always one of the two?
It's always one of the two.
I don't know.
Number 1, what do you think? Exo or endo?
Endo.
Yeah, exo or endo.
Endo.
Two endo. Are you thinking? Because I think if you think you could be able to answer this one.
Endo, expand.
It's not about expanding. What are you doing?
That's work.
Well, I mean, it is about expanding, but what's happening when you
It's taking
expand?
in energy.
Which is endo.
In order to expand or separate solutes from each other, what would you have to do? You're breaking stuff, right?
Yeah.
What would that require?
Breaking nuts.
And then release it.
Energy.
How about number 2? You
Uh,
better get this one
What do you mean overcoming?
right. Breaking.
Isn't that what we were saying the whole time? Endo?
You never said anything until I prompted the specific question. Okay? Now this one.
Exo. Endo.
This one's the hardest.
It's one of the two.
It is.
I wanna-
Good job.
Don't worry, people on
I
camera.
want to know why you think what you
We're
think.
not stupid, we're just tired. I don't know on camera. Oh, we're not, how I'm tired, I don't know that we're not supposed. It's exo.
First of all, it would have to be exo, just from common sense, and here's why. Without even reading that, this is the whole process of dissolving something in a liquid. If the whole process was endothermic, would it ever happen?
No.
No.
And the reason why it's exo is because you're taking the attractive forces of a solute and the solvent and you're attracting each other. Okay, so you're essentially forming those bonds or forming those attractions, and that typically gives off energy. Okay? So, let me see here, what's next? So we do have the enthalpy then of a solution, and I'm going to give you kind of the two energy diagrams that you will typically see. There's your energy. I don't know if you have space to draw this or not. Emily's doing origami. Okay, the first two steps are endothermic. Meaning gains energy, correct? The third step loses energy. So the amount of energy from here to here, what's it called?
The enthalpy of solution. That was a podcast.
Really that wild?
Not really, some little bits of numbers right there, but.
I mean, think about it. If you add all these things together, what do you get? The net. Okay, so let me ask you, is this dissolving or precipitating? Will it dissolve or will it precipitate?
Dissolve.
It's going to dissolve. Why? Why is it going to dissolve?
It's breaking the Lord's bond.
I never said so.
When you drew it, you said it's dissolving.
No, I didn't. So there are two possible things.
Because it ends up with lower energy.
Yes. Lower energy to be less energy at the end than at the beginning. You have a second situation. This one probably isn't going to dissolve because the energy that's given off when a solute is attracted to a solvent isn't enough to overcome the energy that would have to be put in to a particular solution. So I don't know if I should say precipitate here more than I should probably just say doesn't dissolve. Okay, so why is water and oil not mix then? All right, well, let's talk about, let's say the solute is your oil and the solvent is your water. Okay? So if I'm expanding the solute, that would be breaking apart intermolecular forces of the oil. Okay, does oil have high intermolecular forces or low intermolecular forces? Any idea? Oil's nonpolar. No. It would be low normally, but oil is a huge molecule. So it's actually relatively high because it has a lot of dispersion. It's only dispersion, but remember, it's got a lot of electrons that can create that momentary dipole. So it has a relatively high change in H and positive because we know it's endothermic, correct? Okay, now we're expanding the solute for change in H2. The the solvent. The solvent is our water, right? What do we have to expand or break when we do that for our water? It's high, but what are we breaking? What type of forces? Yes, and what type of intermolecular force?
Hydrogen bond.
Yes, hydrogen bond, which we know that takes a lot of energy, so that's also high. Right, does this make sense so far?
Yeah.
We're expanding relatively high solute intermolecular forces because oils are relatively big particles, so high dispersion forces. H2 is going to be high because water has hydrogen bonding and it's going to take a lot to break that. Okay, and this is the attraction between your solute and your solvent. Well, your solute is polar, your solvent is nonpolar. Do you think this is going to be relatively high? Probably going to look like that. Okay, quickly open your books. I have a whole lot more time here. Page 503. I'm just curious if you can identify something here. Okay, so we're going to kind of start just below where it says enthalpy of hydration. I want you to read about that. I was going to just vaguely talk about it, but I'm not going to. This whole section, this whole page is talking about salt dissolving in water. And then the very bottom math calculation there where it has the change of H of solution is 3 kilojoules per mole. That is the change in H of solution for salt dissolving in water. Why is that number alarming? Think about salt dissolving in water.
Sea.
What?
Our ocean.
You know, think about the context of that number and the sign of that number. The 3 kilojoules per mole, 50. Because what? It's endo. Right? Well, last time I checked, salt dissolves in water pretty easily, doesn't it? Okay, so why? Why will it dissolve in water? Let's read. Starting just below that. It says, note that the change in solution is small but positive. The dissolving process requires a small amount of energy. Then why is NaCl so soluble in water? The answer lies in nature's tendency toward higher probability of a mixed state. What does that sound like? High probability of a mixed state. Entropy.
That was the word I didn't have.
You said it right. Your mom said it right away. Entropy. Okay. In fact, we'll talk much more about this concept in chapter 16. Okay. But entropy plays a big part in this. That is, the process naturally run in the direction that leads to the most probable state. For example, imagine equal numbers of orange and yellow spheres separated by a partition. If we remove the partition and shake the container, the spheres will mix, and no amount of shaking will cause them to return to a state of separated orange and yellow spheres. Would you agree with that?
Probably.
Probably.
I mean, theoretically it's possible.
Yeah.
To eventually go back, but.
Okay. The mixed state is simply much more likely to occur, more probable than the original separated state, because there are many more ways of placing the spheres to give a mixed state than a separated state. This is a general principle. One factor that favors a process is an increase in probability. Almost done. We just go to the end of this paragraph. But energy considerations are also important. Processes that require large amounts of energy tend not to occur. Since dissolving 1 mole of solid NaCl requires only a small amount of energy, the solution forms presumably, because the large increase in probability of the state when the solute and solvent are mixed. Now we will talk much more about entropy later, but it is a very, very, very important concept to remember.